So what we're going to look at today is radicals that have variables underneath them and how we can simplify those. There's a couple different ways to do this. Today we're going to look at just one way. And so off here to the side, just to give you a little bit of information about simplifying radicals with variables, the general principle that we are going to use is the fact that if I do the nth root of a to the n, meaning if the index on the outside matches the power underneath, then those are going to undo each other, and I'm simply left with a. So for example, if I do the cubed root of x to the third, that's just going to be x. And that is the idea that we used when we were solving equations. Okay, so if we think about this, if I did the cube root of x to the sixth, then all I have to think about is how many groups of 3 can I make out of 6? Well, I can rewrite this as x to the third times x to the third. And remember when we looked at our exponent properties, we said that when we multiply, we add the exponents. And so 3 plus 3 is going to give me 6. Well, what this does, the cube root of x to the third, that's just x. The cube root of x to the third here, that's just another x. And so altogether, I'm left with x squared. So let's think if we can think of a shorter way to do this. All we looked at is we wanted to know how many groups of 3 can we make out of 6. That's exactly the definition of what we do when we divide. So I looked at this and I said, how many times does 3 go into 6? And the answer was 2, and you'll notice that we got x to the second. So if I wanted, for example, the fourth root of x to the 12th, then what we could see is that 4 goes into 12 3 times. That means I could make 3 groups of 4. So the answer is going to be x to the third. So this is the idea that I want you to keep in mind. Now the question would be, what if instead of x to the sixth, we can go back to this example up here, if instead of x to the sixth, what if it was x to the seventh? You can write this below. I'm just going to erase a little bit right here, okay? So what if this were instead x to the seventh power? Well, how many groups of 3 can we make? Let's think about this the long way again. So I could make this equal to the cubed root of x to the third times x to the third, that's x to the sixth, and then to get to x to the seventh, I would need one more, x to the first. These two are both going to give me x times x, but I can't make a group of 3 out of the power of 1. That's not possible. So that's what's left over. So that has to stay under the cubed root. And so the simplified version would be x squared times the cubed root of x, because that's what's left over after I make all the possible groups of 3 that I can. This is exactly the same as when you did remainder division when you were little. Right here, if I say what is 7 divided by 3, the answer is 2 with a remainder of 1. So notice the number of times that it went in evenly, that was my exponent on the outside, and the remainder was the exponent that is left on the inside. And that is exactly the way that we are going to do this with the variables. So that is the only extra piece that we are adding today. The coefficients, we will simplify exactly the same way that we did yesterday. So let's look here. When we are looking at square roots, then what we just talked about here is we're looking for multiples of 2 for our exponents because I'm trying to make groups of 2. Cube roots, I'm going to be looking at multiples of 3. Fourth roots, I'm going to be looking at multiples of 4 for my exponents to divide out evenly. This is going to be the same for fifth roots, eighth roots, whatever. We're looking for that kind of a power. So let's look at a couple of these examples that we have on here. So for number 9, excuse me, that was a hiccup. I have got to go in 2 different things. The first thing that I need to ask myself is what's the index on this radical? And since it doesn't say, remember we said we're going to assume that the index is 2. So keep that in mind as we do everything here. So what we want to think about is With the 32, we want to split this apart into a perfect square and something that's not. So the biggest perfect square that goes into 32, that's going to be 16, and 16 times 2 is 32. That's what we did yesterday, okay? And the way I like to set this up is I usually set up my square root in the middle, and now I'm going to sort stuff to the left or to the right depending on how I divide out. Whatever divides out evenly, that is going to come to the left of the radical. Whatever is that remainder is going to stay to the right of the radical, underneath the radical symbol. So out of these two numbers that I chose, 16 is the perfect square, and the square root of 16 is 4. So that gets to come out. The 2 is not a perfect square, so the 2 is going to stay under the radical. Now, I'm going to do this in different colors so you can kind of see. Now I move on to the x to the 4th. So I look at my exponents and I say, how many times does 2 go into 4? Well, that one comes out evenly. 2 goes into 4 twice. So I get x to the 2nd with no x's left over, so they don't need to go under the radical. Now, if I look at 9, the y to the 9th, okay, 2 goes into 9 4 times all together, so that gives me y to the 4th. But that multiple is going to be 8. 2 times 4 is 8. That means I have one y left over that does not get to come out of there. And so there is our simplified radical, 4x squared y to the 4th times the square root of 2y. Notice the exponents under the radical, nothing's higher than an exponent of 1, and they shouldn't be, because if it were any bigger, we could divide it again by 2. Okay. All right, let's look at number 10. So again, the first thing we need to do is try to split this into a product of a perfect square and something else. This is another square root here. So see if you can figure out how we would simplify the square root of 324. Now here's something that's interesting that I notice when I start dividing out. So I started off by trying to divide 324 by 81. And here's what I noticed. When I divided by 81, I got 4. But 4 is also a perfect square. So whenever you get two perfect squares like this, what that actually just told me is that 324 itself is a perfect square. It's not one that's on my chart, but if I do the square root of 324 using my calculator, if I just type that in, we get 18. So that one actually comes out evenly. So that means when I set up my radical in the middle, 18 is going to come out to the front. There's no coefficient left underneath the radical because that one came out evenly. Anytime when you divide by one perfect square and get another one, that means that it was a perfect square that you started with. So now let's think about A. 2 goes into 3 how many total times? It goes in once. With how many left over? 1. 2 goes into 7 3 times to make 6, and then that means that I have just 1 left over. So 18 AB to the 3rd is what we get there. Okay. Number 11, I have the cube root this time of 216 m to the 3rd n to the 6th. So what we want to check first is see if there is a perfect cube that goes into 216 or if 216 is on our list. And with perfect cubes, you see that I can do the cube root of 16. We get 6. The other thing I notice here is that the powers of m and n are both multiples of 3. That tells me that this radical is going to come out evenly. So the cube root of 216 is 6. 3 goes into 3 once, so we get m to the 1st with none left over, nothing under the radical. And 3 goes into 6 twice with none left over. So that means we have nothing left under the radical at all. In this case, we just get 6mn squared. Let's do one more example before we start looking at some questions. Let's look at number 12. So the cubed root of 56. So I need to find a perfect cube that goes into 56. Go ahead and take a second to look on your chart and see if you can find that. So what I find is 8 times 7. And 8 is my perfect cube, so that's the one that I circle. Now I'm going to divide up my radical. So the cubed root of 8 is 2, and that 7 is going to stay under the radical just like when we simplified yesterday. So now I look at the r's, how many times does 3 go into 8? It goes in 2 times, that makes 6, so r to the second. And then I have 2 left over, so there's an r to the second left in here. Now, just one more time, what we've done by dividing that out is we've made it into r to the 6 times r to the second. These two add up to 8, but r to the 6th is our multiple of 3. So that's why when we divide that by 3, we get r to the second on the outside. And now we look at the s. So that's to the 4th power. So I say, how many times does 3 go into 4? It goes in once with 1 left over. And so now I can finish my radical, and that's going to be our final answer. We're always looking at the index to divide into the exponents. Okay, so the index is always what we're going to be looking at. Oops. Don't let the negatives throw you off on number 13 and 14, okay? They're odd index, so that's okay. So what I would like to do is have you try number 13, and you can put your answer in and see if you have done this right. So this is what I get. The first thing I look at is the negative 64. That is a perfect cube, so that gives me negative 4 on the outside of the radical. That is the cubed root of negative 64. Now I'm going to look at the index of 3 and the exponent of 10. And so just to be clear again, what we're doing is how many times does 3 go into 10? It goes in 3 times, that makes 9, and when I subtract, I have a remainder of 1 left over. That's why I just have x to the first under my radical. And then I look at 3 and 21 for the y's. 3 goes into 21 7 times exactly with no y's left over. That's why we don't have any y's left in here. Let's go ahead and try to do number 14 the same way. So this one's a little interesting here because when you get to the p, so negative 81 is not a perfect cube, but we do have a perfect cube that goes into it. Remember, when you've got a negative, keep the negative on your perfect so that you get it outside the radical. So negative 3 is what comes out, and then that positive 3 is what stays in. Now, when I look at p, I say, how many times does 3 go into 2? Well, it doesn't go in at all. So that's why when we look on the outside here, none of the p's came to the outside of the radical. They all stayed on the inside here. And then 3 went into 12 evenly, so we get q to the 4th. I would like for you to try 15 and 16 on your own, and then we'll finish this up. Here's the answer for number 15. And here is the answer for number 16. And so that's where we're going to go ahead and stop for today.